Okay, pretty much a general trend in mathematics. Once we learn how to do some new operation, we typically then learn how to undo that operation. So like the first thing you learn in grade school was addition, and then you learn how to undo that. The inverse of that, subtraction. And then you learn multiplication, then you learn how to invert that to go backwards, division. And we're going to do the same thing now. You've learned derivatives. We're going to learn how to undo derivatives with something we call the antiderivative or the indefinite integral. So we're going backwards. Instead of taking a derivative, we're going to say what function's derivative would be this guy that I have in front of me. Now, the problem with antiderivatives is the derivative is not a one-to-one function. More than one function could have the same derivative. So think about these guys here, x squared plus 5, x squared minus 2. Both of those guys would have the same derivative, 2x. So we say, here's our definition of an antiderivative. We say a function f is one of many antiderivatives of a function little f if the derivative of capital F is little f. And of course, for all x in the domain of little f. So there's more than one antiderivative of a given function. In fact, there will be an infinite number of them. And the reason for that is because if we look at these guys here, if I take his derivative, the derivative of x squared is 2x plus derivative of 5 is 0. Over here, derivative of -2 is 0. No matter what number was here, the derivative of it would be 0. So because the derivative of a constant is 0, I could put any constant I want here and I would still have the same derivative. So in most cases, somebody will hand me a function and say, give me the general antiderivative. That means they want an entire family of functions. And we do that by finding any one particular antiderivative. And then we put this plus c at the end. That's called a constant of integration. So if you know an antiderivative, I know x squared is an antiderivative of 2x. That's just one of the many. Then adding some constant c to it, I still have another antiderivative. So we'll call this form here the general antiderivative. Now, I mentioned this way back several videos ago that said, we had this theorem that said if two functions have the same derivative, then they must differ by a constant. That's literally what this line right here says. This line, written a different way, would say, if f and g have the same derivative, then g must be f plus some constant. Okay, and we could see that by looking at some pictures here. So all of these functions here, these is just x squared plus some random constant. These would all have the exact same derivative. Because the derivative of 2 or 1 or -1 or -2 or 137 would be 0. So this entire family of functions all have the same derivative. We would say then that the general antiderivative of 2x would be x squared plus c. And another way to write that, instead of writing out the word antiderivative, is using this notation right here. This letter right here, that's just the letter S. And it's a stylized S, like our letter S from sum. And we'll see once we get into Riemann sums why we write an S here. We read this as the integral or the antiderivative, the indefinite integral of f of x dx. Now, you will never, ever in your life, unless you become a math major, you will never, ever write this symbol right here without writing some kind of differential right here. And this differential tells you what your independent variable is. We'll see where it comes from when we do Riemann sums. But you got to keep this in mind. If I were to write this group of symbols right here, this is 100% meaningless. This is mathematical nonsense, what I've written. What's the antiderivative of x squared with respect to what? You will never write an integral symbol without also having some kind of differential here, d something. In this case, since my independent variable is x, I would have to have a dx here. And in this case, the antiderivative of x squared, we'll get to that in a minute. I'm just showing you notation. Okay, that's a good place to stop there.